So thanks, Blaine, and also thank you, Noeon Research, for sponsoring this. My name is Hoagy Cunningham. I am currently a researcher at Anthropic. I'm mostly going to be presenting research from last year that I did with my collaborators at LU3AI, and that Anthropic did some very similar work on, which I'm now have joined them to work on. And this is finding features in large language models with sparse autoencoders. But before I sort of get into the meat of what that means, I just wanted to take a bit of time to kind of get a bit of a sense of what this field is, because we've been seeing a lot of much more theoretical work. Now we're going to have a few different talks on interpretability. So yeah, I mean, what is interpretability? There is, I mean, it's a pretty huge field of work. Someone recently said to me that interpretability is kind of the science of trying to understand how models generalize. So we know that we're only ever, with any system, going to be able to observe some finite, limited number of cases where this model is acting, and we want to know how to generalize. We want to be able to predict what it's going to do in these other situations. And I think almost everything can be kind of cast as a lot of things can be cast as interpretability. So when we do evaluations, when we try and evaluate how smart a model is, we're getting a sense of how smart that model is going to be in other situations. So we're understanding its generalization. I mean, other things you can go in more detail. You can sort of, for a given output, you can look at the Shapley value of the tokens and sort of get a sense of which tokens have caused the output. And you can even do things just like playing around with the model, trying to understand the contours of the character of the model. And this, I think, is still interpretability, because you are just improving your ability to predict what this model would do just by, you predict a person by interacting with them. Nonetheless, I think, especially because these models are particularly new and weird things, and they're going to be changing a lot over time, we can't just sort of rely on just talking to these things. And there are also lots of situations that we wouldn't want to put them in to even test what they would do. So to get a deeper understanding, we turn to mechanistic interpretability, which is the sort of project of trying to look inside the box. So we have this algorithm, we have this machine learning algorithm, and we know exactly what the code is that it's written on, and we even know exactly what all the parameters are, and we know what all of the vectors inside the model are. Surely we can understand this. It's a very similar project to neuroscience, but it has the advantage that you can run pretty much any test you could possibly think of. You get to start with the exact values of every single parameter, rather than that being a gigantic multi-decade task to map out all of the parameters in the brain. And again, there's lots of types of mechanistic interpretability. So some people would do things like trying to understand the macro structure. Do we find modularity in models? Or perhaps, for example, in transformers, we find that every unit in a transformer is a residual unit. So you will, in an MLP layer, you will calculate the neurons, and they will feed back, and they will add back to the inputs of that unit, and the same for the attention. And so you can see it as consistently updating a single vector, which is getting updated at every single layer. And it turns out you can do things like, just try and take a middle layer and immediately go to the output. And that works pretty well. And so you find that it's a machine which iteratively calculates its outputs in this sort of step-by-step way, which didn't have to be the case. And so you can find some interesting things at the macro level, but what we're really trying to do is more like finding atoms. We want to know what is the sort of core unit of thought that these networks are working with. And, well, one thing you might think is a good idea for these core units is the neurons themselves. They are a neural network. If you're a neuroscientist, you might immediately think this is perhaps not the unit to work with. But to give a very brief history of mechanistic interpretability, lots of the original work was done by Chris Olah and others at Google Brain, and then OpenAI and Anthropic, Nick Camerata and others. And lots of that work was done using neurons as the unit of analysis in vision models. And so what we have here is a description of the kind of the dream of this working. And this is a real example. What we have here is these are 3 neurons in a previous layer on the left, and a neuron in the subsequent layer on the right. And for each of these neurons, we can work out what kind of images would this neuron try to fire on. And you find something that looks a bit like windows, and a bit like car bodies, and a bit like wheels. And on the next layer, we find something that looks a bit like cars. And we look at the weights that connect up these things, and we find it's looking for this windows in the top and wheels at the bottom, and this, seems to detect cars. So this is a really nice example of a clean, crisp story we can tell using neurons as the unit to say, well, how is this model detecting cars? Well, it detects them like this. And obviously, there's more to the story. But that's a pretty good starting point. Unfortunately, when we moved, or when they moved from working with these vision models to transformers, and especially to language models, we find that the neurons just don't seem to work as well. So in the way that we found that these neurons would consistently activate on quite like clustered examples of things. When we look at when this neuron is active, we can understand the kind of semantic cluster. We immediately have a reasonable guess of what kinds of things will activate this neuron. When we go to language models, this is much less the case. There's maybe multiple clusters. Sometimes it just doesn't seem to make sense at all. And so there's this question of, well, why would it be the case that in a vision model, neurons seem to mean specific single things, and in a language model, they just don't seem to mean specific things in the same way? And again, in my very stylized history of Mech and Tup, the second paper is on toy models of superposition, which is an investigation of when you would expect to see this phenomenon using lots of like simple, small examples. And what we see here is we're going to say, well, let's imagine that there are some larger number of features. Maybe there's 100 features, and we're going to try and compress those down into maybe a 10-dimensional layer, a 10-dimensional space. And we're going to say, well, how does it do that? Does it actually manage to represent all 100? Does it even try to represent all of 100 features? Or does it say just pick the 10 most important features and give them all a neuron and we just ignore the rest? And the kind of determining property that they found was whether or not it gives a single feature to a single neuron depends on how sparse those features are. And so what we see here, this is one of their examples. Each column here represents a single neuron, and the sort of little units, sorry, it's not very clear on the screen, but these yellow ones are made up of lots of small little blocks. And what that's saying is that in the top case, this is when the sparsity is 0, so all features are on all the time. What does it do? Well, each neuron just represents a single concept, and if there are any more concepts than there are neurons, we just won't represent them at all. In this other case, we have sparsity is 0.999. So what happens in this case? Well, because these features are so sparse, it becomes advantageous to the model for each neuron to try and represent multiple concepts, and each concept will be spread across multiple neurons. So there's this kind of, this key relationship. We have low sparsity, we have features being on often or even all the time, then they will expect to get a dedicated dimension, perhaps a dedicated neuron, and when the features are really sparse, we'll move to this sort of distributed representations or superposition case where neurons represent multiple different things and the kind of units are spread across multiple neurons. Okay, so given that we have this sort of basic picture in mind, how should we kind of recover it? If we don't want to use neurons as the basis, what should we do? Well, as we've just said, we have this belief that we are now in a model where we have way more features than there are neurons, than there are dimensions in any given activation space. But we also believe that these are sparse. And this makes a lot of sense if you think of what's going on in a language model. I mean, if you think with a vision model, you might have textures and shapes and colors. These things are very common. They exist in sort of most images. When we think about concepts, maybe like people or even just particular words, types of verbs, they're going to be very rare. And so very few of these features will be active at any one time. And so we can convert this almost directly now into a sort of neural network architecture of our own. So we can take our activation vectors, whether this is from an MLP or from the residual, which is where it's added back into the input, we can take that vector, and then we can try and say, well, if we had really knew what the features were, what should we be able to do? Well, we should be able to expand this vector out to a much wider space where each of the dimensions are these new features, but that this wider space should be very sparse. There should be very few of them on, much fewer than the dimension even of the much sort of thinner activation layer. And then we should, because this is kind of all of the information, we should be able to reconstruct the original activation vector from this wider sparse space. So that's the kind of intuition. And we cache this out as a very simple machine learning problem, which is to say, we have X is our input, Our features are a ReLU of just a matrix plus a vector. We reconstruct them with another matrix, and yeah, that matrix can also be thought of as a sum of feature vectors. And then the loss we apply is a mean squared error loss, so we want to be able to reconstruct it. We have an L1 penalty, so this is where the sparsity comes from. An L1 penalty says we're just going to add up all the activations. So if we have two features on, one is on with a magnitude of 5 and one is on with a magnitude of 2, the L1 loss will be 7. And this is a little bit funny because L1 is not really what we care about. What we really care about is just the absolute number of features. But this does not have a good gradient. This is like a very difficult thing to optimize. And there's like a load of research which shows that using L1, optimizing L1 is a sufficiently good proxy that you will recover L0, like properly sparse solutions. So yeah, we use the L1 penalty. This is where the sparsity penalty is applied. And yeah, we can just train this. We can take millions or billions of activations. We'll take a language model, we'll just get a big data set and we'll run the model on it and then pull out these vectors in a particular layer. It can work on any layer, or maybe not attention. Attention needs some extra work. But on MLP and residual layers, we run it through this model, and then we're just going to see what we get out. And we get out a lot of things, and the question is, how do we even start looking at that? And the kind of basic thing you can do is to say, well, okay, now we've got one feature, we've got one dimension in this wider space. What are the cases in which this feature is most active? And so this is from the Anthropic paper, their one-layer paper, and we can see on the left that these, it seems to be activating most strongly on nouns at the end of the word, at the end of noun phrases. There's like a fair amount of clustering in terms of game and station and warehouse. It's not like a perfectly clear unit that we immediately make sense, but it seems to be like quite sort of consistent and clustered. And this is the kind of thing that we see. And as you go to larger models, you start to see much more interesting things. This is not like, in a one-layer model, you're not going to expect to see brilliant structure, but it seems, it's not like a combination of obviously separate things. Now, obviously, just looking at the top activations isn't going to tell you a huge amount. Even in cases like neurons, just looking at the very top activations often looks very clustered. Even when you sort of, dig down into this dimension, there's like lots of other things going on. So we can kind of have a look at that. This is a feature which seems to fire on Arabic text. And so this is a histogram. The x-axis is how much the feature has fired, and this is a histogram of the amount of times that is fired this much. And the red is Arabic text, and the blue is probably not Arabic text. And we can see, interestingly, firstly, that it's not like anything, it's nothing like a Gaussian distribution. We have this big lump. This is, suggesting that we found some kind of just structure, at least. And then we can see that it's quite clearly separating out Arabic text, not just at the very top, but throughout its range. And then we seem to cut off the feature roughly when, it's mostly turning off Arabic, going back to normal text. And there's probably some cases of Arabic text which it doesn't catch, but it seems to be pretty good. So that's a sense of one good feature, perhaps. But we can then use that to say, well, let's understand a passage of text through the eyes of this autoencoder. So this is John Keats's Ode on a Grecian Urn, I think. And what we've done here, we'll run the autoencoder over this whole passage. And I've highlighted the word earth here, and we're going to see which kind of clusters seem to be active at this particular moment. So, and the coloring here is the proportion of the maximum activation of all of the activations we've seen. What proportion do we have at this word? So the highest one is early modern Shakespearean English. So firing on things like words which contain things like thee and ye. And so that's not on this word in particular, but just previously and in the paragraph. So it's tracking as a whole the fact that this is in this very early modern English. We have the second one is labeled sun and says things like celestial bodies. So obviously Earth is a celestial body. And then as we go down, things which are sort of somewhat related, but maybe less exactly clustered, things like grass and farm related concepts, descriptions of nature. So we can get a sense of what kind of clusters the model is kind of treating this input as containing. And again, this is an interesting window into a one-layer model, but it suggests that perhaps for much larger models, we might be able to get some much richer kind of insight into what's really going on there. I mean, one problem you might have with having larger models is, we might find millions of features, we might find tens of hundreds or billions of features. How could we even look at them all? And that's where I think it's a kind of research where we can leverage large language models a lot to like really help us get a hold of these features. So one thing we can do is, and this is following some work that OpenAI did last year, you can say, okay, here's a feature that we've learned. Let's see loads of examples of when this feature was active. Can we then feed that to a language model and get it to give a guess of like, or say a few sentences about when we think this feature is active. And then not only can we get it to sort of describe the feature, but we can test its description, because then we can separately give another language model, just the description and say, predict when will this thing activate? And we can like judge it. We can judge the quality of the feature based on the degree of correlation between the predicted and the actual activations. And so this allows us both to like maybe feel confident that we can actually get a grasp on potentially tens or hundreds of millions of features. And it also allows us maybe, if our protocol is good enough, which I think we haven't demonstrated yet, and we're working on this internally at Anthropic to make these things better, but yeah, to maybe get a judge of like, okay, how good was this sparse autoencoder versus that sparse autoencoder? So I think there's a lot of promise in this kind of, really bringing in the language models to help understand the language models. But kind of stepping back a little bit, I also want to talk about just like, why do we think that we've sort of found something kind of real here? I mean, there's always a danger that we find something that's sort of a cluster. It's an interesting fact about the model, but are we finding something which is kind of fundamental to its computation? And I think this is something this is hard to answer, and I don't think we've necessarily answered it totally. But I wanted to go back to this Arabic feature, and instead on this histogram, what we have is instead of like the context in which it activates, what we have is when this feature is active. This is just a one-layer model. So when this feature is active, which tokens are most up-weighted by this direction? So, this feature is active. We can just multiply through the matrices and ask, well, when is this going to be? What direction does this push the model in terms of its answers? And right on the far right, forming a separate peak, that is the tokens which correspond to letters in Arabic. And they're really quite nicely separated from the other ones. So we're finding that not only is this firing on Arabic, it's not just finding that it is Arabic text, but it's acting to upweight the probability of the subsequent text being Arabic. And not only that, but there is no neuron that we could draw this graph for. You could look over any number of neurons. We could look through every single neuron, and there is not any neuron which separates these out nearly as cleanly. Not in terms of the logic weights, and not in terms of the being able to just detect the Arabic. So I think that's an indication that we are really separating out not just what's in the space, not just the information in the space, but what the model is actually doing to act. How is the model doing computation? I think there's a lot more to answer in that case, but I think this is just one indication that we are at least pointing towards something which is kind of true and important about the model. In terms of how we would go further, obviously this is just finding a sort of cluster in the model. So we might say, we've found a feature in the model which is active if a person is lying. Now we might care about that. We might think if the model is thinking that it's lying itself, that would be interesting. But what we really want to know is how is the model going to act on these features, and how is it going to sort of build them up over time? And this is still definitely a work in progress. And in fact, there's been some really interesting work really developing this in the last week, which I haven't had time to look at, by Sam Marks. But this is from our paper. This was our kind of initial version of looking at this. And we'd find this was on a 6-layer model. We'd find in the last layer, there was a feature which would particularly make it likely that a closed bracket would be predicted. So, we're going to predict a closed bracket. Well, which features cause this? Well, in the middle layers, we find things which are, I'd say at the top we find features which just detect the open bracket, and then we can find that those influence later on in the model, and presumably later on in the token, in the text. We find features that will track whether the open bracket, we are within a bracket, and then later on we realize, now it's time to close the bracket. And so we can't flesh that story out in perfect detail, but we can get a sense of how it like builds up the complexity from sort of recognizing inputs to like tracking longer term kind of things about the model, and then into like converting that into action. So this is just like a very early kind of idea of how we might get some more serious statements about what this model is really doing. So that's our kind of like basic picture. I think we're learning something really interesting, but there's a lot to do. So this is just like a set of things of what we're going to try and do next. So like I was just saying, we want to do circuits, and there's been some great work of that literally this week. There's like a lot of really, really fun things coming out from various different labs and independent people on this kind of work now. We also just want to train these things better. We want to train them to huge models, and we want to get the right hyperparameters. And you know, there may be many like tricks and tweaks, and maybe it's not even the exact right kind of formula for training. We also don't really know if we can apply these ideas to attention properly. And interestingly, we still have like, I don't think, the perfect understanding of what we are finding. So like one thing, like early on we said that there's, in the vision models, there is something which really pushes features to be concentrated in single neurons. And we would expect there to be still some kind of pressure, even in language models. They might not be on a single neuron, but they might be on 10 or 20, not like all neurons. Whereas what we actually tend to find in these layers is something which is like totally spread out. So I think that's just one maybe pointer towards the fact that we don't have a perfect understanding of what we're finding here. So yeah, lots of future work to be done, scaling and training. It's kind of time for questions. I've given some pre-Q&A questions for just sort of general things that I didn't really cover. The first one is like, this assumes that everything is linear. Like if a feature is not linear, it won't be picked up by this model. Is this not a dangerous assumption? And I think Oscar is talking about linear representations immediately. I would just say there's been a lot of interesting work from Oscar and others, like showing just how many rich things can be represented linearly, not just like features in the sort of classic sense, but even like tasks. You know, when we ask a model to do something, the nature of that ask can even be represented linearly. And what have we really learned about the model? You know, we're grouping these things together. We definitely need circuits. And when do we think this might help? I think there's lots of cases. I think we might just learn more about the model because it's just such a mystery. It's such an open door at the moment. I think especially perhaps it would be really good, like companies are starting to offer fine-tuned versions of models, and we want to have a really quick way of like understanding what changes are made when you fine-tune a model. And I think this maybe can provide an answer of actually what has been changed in the model when we've just given it these few examples. As well as, yeah, I mean, I think if these really are the atoms, I think there's almost an unlimited number of things we can do. So I think it's a really exciting thing. Anyway, those were my quick questions, but your questions.
Let's bring the lights up. Yes, straight away from the front center.
Yeah, thank you for the nice talk. So you're essentially trying to like decode these features which you assume are sparse, which are then somehow stacked through the superposition in the real model, or in the trained model then. It would be interesting to hear your thoughts on like the choice of sparse autoencoder, and especially the size of like the middle layer, and what happens if you like have too large one, or when it's too small, and if you could comment on that failure modes in either case.
Yeah, so this is a really great question. I mean, I think what we kind of hoped to find initially was something that I could have covered here, which was, we were hoping that there would be a discrete number of features. So if it was too many, maybe things would go wrong, or maybe they would just like never turn on. That would be the sort of easiest version, and maybe if there were too few, I don't know, it wouldn't quite work properly and somehow. I think what we find instead is that it's much more smooth. You know, we make it as wide as you want, and sometimes these things, because of the sparseness, it's quite easy for features to die, because they'd get to a region where they just never have a gradient. But assuming they haven't actually died, which is more of a training failure mode, it seems like it just continually finds like more and more and more fine-grained distinctions, which is, I think, maybe an evidence that it's not quite, although we are finding something about the clustering of the model, it's not the sort of perfectly discrete set of features that we might have hoped.
Could you pass the microphone back and to your right to Kai?
Hello. Hi. So if we want to do mechanistic interpretability on multimodal models, so say it's taking audio, vision, text, as input, do you expect you'd want to be using different methods based on, say, the layer or depth you're looking at, or would it be more based on the natural distribution of properties in the data, like, as you said, like spatial vision, natural images contain different distributions to text data, and then finally, if you had a sort of multimodal space towards the end of the model, like what sort of methods would you be using to something that's integrating like information from all of these different modalities?
Interesting question. I mean, I think, so I guess with vision models, we've seen that, like, especially in the early layers, like just looking at the neurons seems to be pretty good. I think there's like some really interesting work that hasn't yet been done, which I would love someone to do, which is to compare, like, at what point does it seem is there a crossover, or how well does sparse autoencoders work in this kind of early vision sense? When it comes to audio, Eleanor Reed did some interesting work on the audio models, and like found that you could like find syllables quite nicely in the residual stream in a way that you couldn't necessarily discover otherwise. So I think these things seem promising for at least the inputs. I think, like I alluded to, I think theoretically it seems like we should want to adjust perhaps something about the way we're doing for the sort of statistics of the neurons and how sparse they are, and I don't think we necessarily know how to do that. So I think there may be some adjustments to the kind of techniques that we would make if we knew how. But I think at the moment, like, this does seem to be the kind of best technique that I know of, at least, regardless of model layer or depth.
Okay, I think that is sadly. I think we could do one more. We can do one more. If you head to the.
Hi, thank you. This is a follow-up to the previous question. Have you tried things like checking the goodness of fit, when you are doing the encoding and then the de-encoding? You're basically, and then you check how well you've been able to decode the original thing that you encoded.
How well does that work, basically?
How well does that work?
Yeah, great question. It really depends on the model. I think with their one-layer models, which have some kind of advantages because there's kind of a natural sparsity that's induced by just the fact that the tokens are just there, and generally in early layers, you can really get it down pretty well. I think the measure we often use is not exactly like, where you can say sort of proportion of variance recovered or something. What we often do is like, if we like ran the model forward, but using our layer instead of the actual layer, or like going through our layer as well, like what's the loss? How much do we lose in terms of model capability relative to just having taken out that model, taken out that layer entirely? And for this one layer model, you can get up to like 95, maybe even higher percentages. For the like middle layer in a sizable model, generally at the moment we're looking more in the kind of 80-90 range, 80-90%. So there's definitely some somewhat sizable losses, but it's a pretty large chunk of.
Because I guess that can help you address how wide you need to make the internal layer.
I mean, it's definitely a good point that we would love to. I mean, ideally, there would be a point we could sort of draw this line, and then we're like, oh, maybe this is how many we need for perfect reconstruction. At the moment, it's kind of like more of it sort of flattens out, and often it flattens out, quite aggressively, where like going from like 1 million to 2 million features doesn't necessarily give you that much. And one of the big questions that I'm working on at the moment is like, okay, given we're doing that kind of work, is that because we just aren't good at optimizing it, or is that something fundamental? And that's quite hard to figure out.
Thank you.
Okay, thank you, Sam. And thank you, Hoagy.
Thank you, Blaine.
Great talk.